Welcome to lecture number 3, part 2 in the course on process control. I'm Gustav Olsson from Lund University in Sweden. And let me now show you the slides. My co-authors in this course are Pernille Ingeldsen from Hillerød Utility in Denmark and Bengt Karlsson from Uppsala University in Sweden. In this lecture, we have talked about sensors and instruments and actuators in part number 1. And in this part number 2, we'll talk about monitoring and supervision. In other words, how to transform data to information. Looking at the extraction of information, of course, we first have to acquire the data, storage the data, and make it available for further analysis. The first part is data screening. In other words, remove irrelevant information. That can be noise, that can be outliers, it can be missing data, and so on and so forth. And we'll see examples of how to do that. And the next one, having got the information, now when it's available, we try to find something that is not normal in the operation. In other words, detection of abnormal features or effects. Having detected that something is going wrong, then of course we have to find some diagnosis, what to do, what is causing this problem, and that can be the basis for a decision. So the information extraction contains several layers of analysis of the available data that you get from sensors. So monitoring, that means, first of all, to track important variables and to see, do they make sense? Do they deviate a lot from some kind of baseline or normal behavior? And then this creates the basis for an updated process state information. Detecting the deviations in the performance of the process, we will show how that can be done. And then, of course, what is the reason for the deviation? That is part of the diagnosis of the system. So we all the time look for abnormal behavior. And as long as everything is green, in the sense that everything looks healthy, then we don't need to worry. But the computer is awake all the time, and it doesn't take any coffee breaks. And that means the computer can really watch what's going on. And as soon as something abnormal happens, it will give some kind of alarm to the operator or the process engineer or the one that is responsible for the operation. Now, let's first look at data screening. Is the data biased? Does it have a good precision? And this is part of the data screening process. Looking at this DO controller performance, for example, during a number of hours, about 2 days, 2.5 days, you will see that we try to keep the DO at a level of 2.5 milligrams per liter. But of course, sometimes we see deviations, and we have to find out what is the reason for it. Is it calibration of the sensor? Is it something else that is causing a bigger deviation from the sort of normal noise that we can see in the signal? So that gives us some kind of indication of the performance. Another test could be looking at the influent flow rate. This is the influent flow rate in the plant during 3 weeks. And you will see here the average value, the mean value is located here. The 2 sigma value is indicated in the dotted line, and the 3 sigma value. And of course, now we see something odd is happening here, far above the 3 sigma limit. What is really going on? Is it a real problem with the flow rate? Does it have to do with the sensor? What is the problem? Likewise here. So we have indications. Well, we may accept up to 2 sigma, but not 3 sigma. Sometimes this is called statistical process control. And this is a misleading term because there's no control in it. It's simply an observation about the deviation of the signal from normal or from the mean. So there is no control action in this, no decision being made. Another one is, of course, to detect missing data. And we can see here suddenly the flow rate is equal to 0, and likewise the concentration in the effluent is also going down like this. So of course, if you send this kind of signal into the controller doesn't know if this is a real value or if it's a missing value. So therefore, it's important to screen the data before it's sent to the computer for a control action. This is a very special case. It's the effluent from a secondary sedimentation unit. And the first time was very strange behavior, because you can see here that there is a spike in the data every 15 minutes about. Well, what's really happening is that the scraper on the bottom of the secondary settler is moving around 1 revolution per 15 minutes. And that means that every 15 minutes, there is a big chunk of sludge coming to the sludge measurement. Now, in the first case, people measured the sludge concentration every 10 minutes because that seems to be a reasonable sampling frequency. But data was very strange, sometimes very, very high, sometimes very low. And in reality, it doesn't look like that. So sampling here means that the true value in the secondary settler is some kind of average value, and you can see some kind of slow trend in a few hours. And it doesn't change on a minute-to-minute basis. This depends on the machinery, on the sludge scraper. So in other words, we have to know something about the process when we decide about the sampling rate. There's also some kind of trends in data, and the total Chelldal nitrogen is looking like the dotted curve and the ammonia like this. And they have trends in them, and the trend can be removed. And if it is adjusted, then we can see that the concentrations are related to each other. Or the influent flow rate. Well, this is the flow rate during 2 days in a plant. And of course, you can see the apparent peaks every morning and some smaller peak in the afternoon. One way to look at this data is to make frequency analysis. In other words, which are the dominating frequencies? And then you can see that every 24 hours, there's a very clear marking. Yes, there is a daily variation, but it's also a variation every 12 hours, as you can see in the second peak here, between the morning and the afternoon peaks. So in this way, it's possible to have other kind of information about the influent behavior. This is data of raw nitrate data. And you can see outliers here. There are sudden peaks downwards. And of course, this is not a real change in the concentration. And that kind of signal shouldn't be sent to a computer for a control decision. So we have to remove the outliers. How do we detect if it's an outlier? Well, one very apparent way you see here that the rate of change downwards or upwards is very, very high compared to what you could expect normally from nitrate data. And if you filter the nitrate data, it looks like that. you take away the outliers. So in other words, screening becomes very important. Another way to do that is to use what we call a high-pass filter. And as I said just before, you look at the rate of change of the signal. And the rate of change is very high when the outliers appear. A very high positive change or a very high negative change in combination. And that is a typical detection of an outlier. The next point after the screening, removing these outliers, removing the trend and so on, also to see, is it worthwhile to remove the noise? Because maybe the noise doesn't give us any information of what's going on. And there are two standard methods that are typically used in treatment plan. One is moving average. In other words, the y-hat here is the estimation of the previous measurements up to n measurements. And we can see one example here. This is a simulation where the blue straight line is making a step from 0 to 1. That's the desired. But the blue dots is the noisy signal that is going from the 0 level up to the 1 level. If you will now take the moving average value, in other words, the estimated value in the red curve is the average of the last two measurements, then you will see that we decrease the noise and we can follow the step change fairly well, and then we decrease the noise, but still the noise level is very high. So let's see what happens if you take the last 20 values. Then you will see that the noise level here and also down here is reduced significantly. But the price we pay is that the filter now reacts very slowly, because not until here, when you have taken the average value of the last 20 sensor values, you will reach the new level. In other words, this filter is efficient to remove noise, but it's very inefficient to detect sudden changes. Well, can you do better? Well, here's another one, the so-called exponential filter. And it says that the estimated value is equal to the previous estimated value times a parameter called alpha, which is between 0 and 1, and the true measurement value. So in other words, you take the new measurement into consideration. And look here, if alpha is equal to 0, then this term becomes 0 and this term becomes 1. In other words, the estimated value is equal to the measurement. So there is no filtration. If alpha is equal to 1, that means you don't care about the last measurement. You just say the estimation is the same as the previous one. So apparently, alpha has to be somewhere between 0 and 1. Look at the same simulated data. The blue dots are the so-called real measurements. And now we try alpha is equal to 0.5. That means that the estimated value says, okay, I weight half of the value is equal to the previous estimate, and half of the value is equal to the last measurement. And then you can see we reduce the noise level again, and we follow the real change fairly well, and we reduce the noise level, but not very much. Maybe we can do better. Well, use alpha equal to 0.9. Then you say, okay, I don't trust the measurement very much. I give it a weight of only 0.1. I trust the previous estimate more, 0.9. Then you can see, yes, I reduce the noise, as we did in the moving average with the 20 measurement point. And we don't react to the true change in the measurements because we don't trust the measurements. So can you find a compromise between the two different exponential filters? This one, 0.5, this one, 0.9. Well, you can do better, actually, and this alpha actually can be made not constant, but variable. But that brings it to a further sophisticated filter. But we can actually find a filter that reduces the noise, as we have done here, but also is sensitive to real changes, so that it would follow much closer to this ideal straight lines. So there's a whole science in signal filtering where you try to remove unnecessary or uninteresting noise, but still being aware of the true signal changes. So remember now that the measurement data is not only for recording, but for control. The controller, the computer, couldn't accept outliers, couldn't accept missing data, because that means that the control action will be completely wrong. We make statistical analysis. We look at one signal at a time. We look at abnormal data. We filter noise, unnecessary noise, uninteresting noise. And in this way, if we make a more elaborate signal analysis, we have something that we call soft sensors, parameter and state estimation. In other words, we can calculate things that we couldn't measure so well. Monitoring now, it contains several different activities. Looking at the real plant here, it is subject to disturbances, both external disturbances and internal disturbances that we have talked about before. The measurements from the real plant are going to the analysis block, and also the observations are going to the analysis block. You can take into consideration all of that in the signal analysis, in the data screening. Having analyzed the data, now we can detect what is causing the problem, and that may give some signal how to change the control action to the real plant in order to compensate for this kind of disturbance or deviation. So these are the elements of what we call monitoring. Let's look at one signal here. The upper curve is a sensor signal, and the lower curve is a signal variability. In other words, the rate of change. And you see in the beginning here, the rate of change is relatively low, but suddenly the rate of change increases a lot. And you can see also on the signal itself, it's suddenly becoming very noisy. So what we do is to use the variability as a detection of a problem. So when the signal variability increases above the red line, then we know that we have a sensor problem. We can send an alarm signal. Something has to be corrected in the sensor, being it calibration, being it dirt coming to the sensor, whatever it is, we have to take care of the problem. So the alarm is sounding automatically. So we have a number of analytical tools here. And you see on the bottom here, we have a time scale all the way from seconds to years. In the slow time scale, we have filtering, we have the outlier detection, we can repair data sets, bring in data to replace missing data, for example. We have the statistical process control, that is statistical analysis of the signal. There's no control element in it. So it's a misnomer of that term. In the longer run, we have a number of mathematical tools, regression analysis between two signals, between several signals. We can make diagnosis. We can have simple dynamical models to compare with the real behavior. And of course, we have different models of the biology of the hydraulics in the wastewater treatment plant, where we can define if there is a similarity between the model and the real plant. And now we are approaching something that is called digital twins, that we will talk more about in lecture 4. Let's now look. Can you see the relationship between several variables? Because very often we see that several variables are related to each other. So a problem in one variable may appear as a problem in the other variable. This is an example where you have 3 different measurements, and you take measurements in a slow time scale. 1 point here means 1 value in x1, 1 value in x2, and 1 value in x3. And as the operation continues, then you will see a number of dots creating that cloud of dots of measurements. And of course, now this can be extended even to 4, 5, 10 dimensions of variables that are related to each other. What we do now in what is called principal component analysis is say, okay, how much of the variability is now along one axis only? Well, maybe that can explain a little bit about the variability, but there are also deviation from that line. But if we instead try to say, okay, can we find a 2-dimensional plane that where you can project the different measurements on that plane, and maybe 80% of the variations can be located or can be seen as located in that plane. And that means instead of detecting 3 variables, you can detect 2 variables. That is the main meaning of principal component analysis. And PCA is part of what we call multivariable statistics. In other words, the relation between many variables. And that's a group of methods. PCA is one of them, meant to investigate how many variables relate to each other. Not only that 2 variables are correlated to each other. So it's a kind of correlation between many variables. And they are often highly correlated. So the true dimension, as you saw in the example of the PCA, may not be the 3 dimensions. It may be 2 dimensions, because most of the variations can be explained by variations along that plane. Take one example here of PCA analysis. Here is a long time series of actually you have 12 different variables, measurements from the plant. And the 12 variables now are projected only on 2, what we call principal components. We have found a plane in 2 dimensions that will basically explain quite a lot. And you can see here that in most cases, most of the dots, they are located within that circle or ellipse here. But some cases, they get outside and they get out. And here we don't know why, but we get a signal. Something is not normal any longer. And having got that kind of information, that is the first level of the alarm. And after that, you can analyze more what happened in the different 12 signals. And now you can see much more clearly that something was going on that was outside the normal behavior. Cluster analysis is a similar kind of methodology where you find that most of the dots here, 1 dot here, is measurements of several variables in 1 time instant. And now the 12 variables are projected on a plane in 2 dimensions only. And you can see most of them are within that kind of area A here. Well, some of them are outside what we call normal behavior. This, after an analysis, found out this after a long period of rain. And of course, that can be seen now as, for example, the suspended solids concentration in the effluent. Or here, there's both a high flow and high air demand. In other words, there is a big increase in the oxygen demand, or high suspended solids in the effluent. And we can see now that, yes, we got a primary alarm signal, but it also means that going from that indication, we can now analyze in more detail each individual signal. And that is done here, for example. You can see the influent flow rate has a sudden change here at that time, and the air valve is increasing. In other words, the oxygen uptake rate is increasing suddenly because of the higher influent flow. And in that way, you can go from here to there by and having a quicker alarm than you would get by looking at all the different measurement values. Because as the number of sensors increase, we will also see an increasing amount of analysis necessary, and we have to streamline the analysis as much as possible. So there are several multivariate statistical methods available. They have different names. I showed you the principal component analysis, PCA, but in some other areas, it's called factor analysis, and it's very closely related to PCA. In other image analysis, for example, it's of course the Hotelling transformation. It's also related to PCA. So it has several names, but the principal idea is all the time the same, to project several dimensions into fewer dimensions. In chemistry, it's principal factor analysis. Again, similar methodology. And then there's another one related to PCA, but a little bit different, principal component regression or projection to latent structures. So all of them have a similar kind of idea, because they assume that some of these many variables are related to each other. They are correlated. And that means the true dimensionality is not, for example, 10. It may be 7, 5, 3, 2, depending on the analysis that you reach. So using multivariate statistics, it's the relation between many measurements, and it's a decision support system. It helps the operator to start, yes, something is happening, we have to analyze further. And this is part of data mining, to extract knowledge from the data using databases, using available measurements. So to summarize, we have talked about monitoring, but monitoring contains several steps. You have to start with data screening, remove missing data, trends, outliers, and so on. You have to remove high frequencies, as we did with the low-pass filtering, moving average or exponential filter. But you can also use high-pass filtering, as we did, looking at the rate of change, and then you detect the noise, and you can also detect the outliers. So monitoring means that you detect any abnormal behavior in signals, between two signals, or between many variables. So this is crucial in order to have a reliable information for the final control decision. So this will finish now the part 2 of lecture 3. In case you're interested, here are a couple of recommended extra references on top of the chapter you have already seen in the book on biological wastewater treatment. So thank you very much for listening, and welcome to lecture 4, where we will talk about plant-wide control, looking at more than one unit process at a time, looking at the complete control of the whole system. Bye-bye.